From time immemorial, man has endeavored to find regularities in the way the world behaves. Scientific laws are based on observations, or else they result from theoretical assumptions concerning a particular phenomenon. The laws are considered valid until they are refuted by different observations or new theories. So-called classical physics was founded on these principles. Light was the object of scientific debate more than almost any other phenomenon. In around 1704, Isaac Newton postulated that light was made up of particles. Christian Huygens, by contrast, declared that light consisted of waves. Newton's model eventually came to be accepted until the English physicist Thomas Young was able to prove the opposite. He was able to show by experiment that light spreads out in a similar way to disturbances in water in the form of waves. But what about the phenomena that classical physics couldn't explain? The man who was eventually to knock classical physics off its plinth was at the same time one of its most ardent defenders, Max Planck. Max Planck was born in the northern German city of Kiel on the 23rd of April 1858. He was the sixth child in a family where values such as respect, honesty and reliability were writ large. In 1867, his father, a professor of jurisprudence, was offered a post at Munich University. Here in Munich, young Max attended the Maximilian High School, where he stood out on account of his hard work and sense of responsibility. He was a versatile and talented boy. His great passion was the piano, as it would be for the whole of his life. In 1874, he went to Munich University to study physics, although one teacher had tried to dissuade him, saying that there was nothing left to discover in this field. 3 years later, Planck transferred to the Friedrich Wilhelm University in Berlin. Here he went to lectures given by Hermann von Helmholtz and Gustav Kirchhoff, two of the leading physicists of the age. Planck was especially interested in thermodynamics, which was to be the subject of his doctoral dissertation. After occupying posts at Munich and Berlin universities, he was offered the post of head of the Institute of Theoretical Physics at the university in Berlin. In the late 19th century, electric lighting was becoming a mass market. In order to develop quality standards for light bulbs, physicists were interested in the laws by which heated bodies emitted radiation in the form of heat and light. Classical physics assumed that as a body got hotter, its radiation in the form of light must also increase. But closer inspection revealed this assumption to be false, or at least inadequate. An example: if steel is heated, it glows in different colors according to the temperature. What is happening here is the transformation of heat energy into light energy. According to the notions of classical physics, the steel should emit more and more light energy as its temperature increases, until finally it starts emitting ultraviolet radiation, which the human eye cannot see. In other words, the steel ought to become invisible. But this assumption of classical physics could not be confirmed by any experiment. The steel always remained visible. Scientists were irritated by this apparent contradiction. Planck was one of many who tried to explain the radiation processes. He spent 5 years trying to explain the phenomenon using the instruments of classical physics. But he found no satisfactory solution. In his desperation, he threw out all his previous convictions and assumed instead that the radiation was not emitted continuously, but in the form of discrete packets of energy known as quanta. This quantization of radiation energy is analogous to water flowing in droplets rather than in a continuous stream. The total energy can then only amount to a multiple of his quantum of action, a constant designated by the letter h. Planck's law states that the radiation energy is the product of the constant h and the frequency of the radiation. While the frequency and the energy were well-known quantities, Planck's epoch-making achievement was undoubtedly the introduction of the constant h. Planck himself was a theoretical physicist. He therefore relied on the results obtained by experimentalists in order to test his theory, but they were indeed able to confirm his assumption and even come up with a figure for the constant, which is tiny. H equals 6.626 times 10 to the minus 34th joule seconds. At the meeting of Germany's Physical Society on the 14th of December 1900, Planck announced his law of radiation, referring to the constant that was later named Planck's constant in his honor. This day was to go down in history as the birthday of quantum physics and usher in a new age in science. In opposition to his innermost convictions, Planck had, by the introduction of his constant, found that nature proceeds by leaps and bounds. He was deeply disturbed by his finding, and like most of his colleagues, he could not really believe it. He secretly hoped to discover, sooner or later, a new law of radiation, which would be in accordance with the principle of the conservation of energy, and make the constant unnecessary. After all, his life as a scientist was rooted in classical thermodynamics. That was where he wanted to be. In the following years, he gave more attention to the numerous matters of scientific policy, with which he was concerned in his various official capacities, as a member of the Physical Society, as rector of the Friedrich Wilhelm University, and not least as secretary of the Prussian Academy of Sciences. After the First World War, Planck was awarded the Nobel Prize for his discovery of the quantum of action. But we owe more to Planck than just his constant. Another discovery was equally important, namely the discovery of a genius in the person of Albert Einstein. At the time, Einstein was working in the patent office in Bern in Switzerland. His special theory of relativity had attracted Planck's attention and moved him to publicize it amongst the physicists in Berlin. But Planck had not only recognized Einstein's genius, he also played a major role in getting him to join the Prussian Academy of Sciences. In spite of many differences of opinion on scientific questions, Planck and Einstein were united by a deep and long-lasting friendship. In 1905, Einstein used Planck's quantum of action to help explain the photoelectric effect. He was thus the first to interpret and apply Planck's constant correctly. So what is the photoelectric effect? When light falls on a metal plate, it is capable of dislodging electrons. It can be demonstrated that violet light, in other words high-frequency light of shorter wavelength, can do this, while low-frequency red light cannot. And it does not matter how much red light falls on the metal plate. This phenomenon cannot be explained by the wave theory of light. So Einstein assumed that light must be a stream of particles known as photons. Each photon imparts its energy to precisely one electron. If this energy is sufficient, the electron will be displaced. Photons of violet light have a higher frequency and thus greater energy than photons of red light. As a result, a single violet photon can do what countless red photons cannot. In order to calculate the required energy level in each case, Einstein hypothesized that the energy of the photon was, like radiation energy, also the product of their frequency and Planck's quantum h. The American physicist Robert Millikan was able to prove this theory by experiment, and in 1921 Albert Einstein was awarded the Nobel Prize for the discovery of the law of the photoelectric effect. Albert Einstein's application of quantum theory showed that light acted both as a wave and as a particle. The old dispute about the nature of light was thus a thing of the past. And gradually, as quantum theory came to be successfully applied in other spheres, scientists came to abandon their misgivings. The Danish physicist Niels Bohr used the idea of the quantizability of light in order to explain the stability of atoms. According to the existing model proposed by Ernest Rutherford, the atom consisted of a positively charged nucleus and negatively charged electrons in orbit around it. The stability of the atom was based on the premise that the attractive forces between the opposite charges are balanced by the centrifugal force of the electrons. Because of their movement, however, the electrons must be continually losing energy and thus be slowing down. Sooner or later, they would crash into the nucleus. But atoms are stable. Bohr was trying to find out how. He assumed that electrons do not circle the nucleus haphazardly, but in precisely defined orbits, in which they cannot lose energy. Nearer the nucleus, the energy levels are lower than in the outer orbits. If an electron now jumps to a higher orbit, it must absorb a quantum of energy, in other words, a photon. When it jumps back, it emits the energy quantum once more. This is the famous quantum leap. The energy emitted or absorbed each time corresponds to the product of Planck's constant and the frequency of the photon. Bohr's explanation meant that the quantum theory had finally established its credentials. With his quantum of action, Max Planck had laid the foundation stone for a new kind of physics, underpinned by Albert Einstein and not least Niels Bohr. It was their research that ultimately created the basis for the development of quantum physics, which explains the processes in the microcosm of atoms and even smaller particles. We owe many of the achievements of modern everyday life to quantum theory. The computer, for example, and the laser with its many applications. Without quantum theory, modern medical technology would be inconceivable. For example, magnetic resonance imaging. It allows pictures to be made of the whole body, sparing the patient the discomfort of multiple examinations. Positron emission tomography allows us to see the metabolism at work. This procedure helps to locate cancer cells, as it can distinguish their metabolism from that of healthy cells. A further application of quantum physics is the ongoing reduction in size of the building blocks which make up computers, which, as a result, will become even faster and more powerful. The foundation for all these technical achievements was laid by Max Planck, with the discovery of the quantum of action at the start of the 20th century.